Hi, my name is Evan Strasnick, and this talk is titled Coupling, Simulation, and Hardware for Interactive Circuit Debugging. Simulation is a powerful tool in the design of analog circuits, and most often we use it before building out real components in a prototype or a PCB. We do this to verify a schematic design. However, simulation also has the potential to aid as a debugging tool when working with that physical hardware. Specifically, it can help the designer to compare their measurements to theoretical expected behaviors to identify where errors may first arise. They also offer a way for the designer to quickly explore alternatives without modifying the hardware, so that they can reveal how changes to the design improve the behavior. But there are also challenges in making comparisons between the simulation and the physical circuit. When the designer adjusts the hardware and measures a response to some input, they have to perform that same change in the simulation, capture the input they observed, and import it into the simulation. Similarly, when the designer explores alternatives quickly in simulation and wants to compare back to the hardware, they would need to manually rework that physical circuit for each case explored. So we address these challenges in a tool called Pinpoint. Pinpoint tightly couples the designer's physical circuit with its simulated counterpart to facilitate debugging. Pinpoint is built on the infrastructure of Pinpoint, a PCB debugging tool we introduced at SIGCHI in 2019. Pinpoint generates for the designer a custom jig board that interfaces their PCB to testing hardware, allowing the user to perform their debugging operations in a software interface as opposed to manipulating the hardware. Pinpoint uses new testing hardware capable of modifying physical components within the circuit and routing external components in their place. Pinpoint software then also manages the simulation of the user's circuit, represented as a SPICE netlist. At the highest level, the first thing that Pinpoint enables is comparing live measurements from the hardware with the expected behavior as predicted by the simulation. As an example, imagine you have this very simple RC filter circuit, which attenuates high-frequency noise. Suppose we have a fault and the capacitor's value is outside of tolerance. When we hook up the circuit to an input, here a sine wave shown in red, we can see that the output, in cyan, is attenuated. But is this filter working correctly according to the parameters of our design? With one command, Pinpoint takes measurements across the full circuit and juxtaposes them in an interactive plot with the responses to the same live input as predicted by the simulation. So we can see here how our physical circuit's output, that's shown in purple, differs from the simulation, shown in light blue. Pinpoint also makes it easier for me to make changes to my physical circuit and its inputs, and when I do so, the simulation updates in parallel so that I can continue to compare behaviors. For example, it can programmatically substitute a physical component on the board with a different component from an external bank. As an example of that, here I can use this modify resistor command to change R1 in my physical circuit to a different resistor value, and as I do so, we can see the circuit update in real time. When we repeat that comparison, we see that the simulation has updated as well. So this ability to modify the hardware helps us to mirror on the hardware the explorations that we typically perform in simulation. For example, Pinpoint gives us automated tools to directly investigate how these alternative circuit parameters affect behavior. So here we can ask how the amplitude of our output varies with the value of the resistor. And with one command, Pinpoint rapidly samples different values of that resistor, measures the responses, and plots those results, here in green, alongside the simulation in red, at those values. And we can see that the output varies inversely with the resistance in both cases, but with a different coefficient because of that incorrect capacitance in the circuit. So please check out the paper for many other features of Pinpoint, such as summarizing high-level patterns across the circuit, automatically detecting relationships that may indicate error, and a specification language for authoring tests on high-level behaviors. The paper also includes demonstrations to show how these capabilities can be used in context to solve a variety of real-world bugs on different types of circuits. And thank you very much.